I'm going to start with a slightly different slide. This way everybody will have a URL they can go to. Right.
Okay. Right. So good afternoon, everyone, or good morning, as the case may be. So a couple of weeks ago, our last talk was from the East Coast, no, from the West Coast of Canada. Today we are in similar time zones, I understand, in California. So good morning to Ryan. This is a talk about databases on the face of it, but there is category theory and rewriting in there, so it's clearly a good fit to what we usually do in this seminar. We used to have a talk here, a couple of talks by Uwe Wolter from Bergen in the spring, for example, on generalized sketches, which are also related to the way that the database kind of query language works, as far as I understand, but we'll hear about that, I'm sure, from Ryan. So Ryan has a sort of illustrious academic career behind him at sort of various top US universities, studying there, doing his PhD, and then working as a researcher there. But now he's running at least one, if not two, startups, if I understand the CV correctly. Maybe he can tell us more about that, by basically making sort of database technologies based on category theory. Yeah, and so I'm not going to take any more of your time. Ryan, please take it away.
Who's the other startup? Is it Stakebox or Fabrizio's company? Or yeah, I guess I'm curious who you think the other applied category theories besides Conexus are, like which companies?
Maybe I just misread the text here that you were involved in several projects. May only be one startup, several projects.
Gotcha. Yeah, so I did a lot of data integration at IBM back in the day, and so like this is kind of a mixture of the academic stuff. Yeah, with David Spivak at MIT on like category theory, and then like data integration, how companies like IBM and Microsoft do it. So, yep, that's my background. Thank you for that. I guess I'll go ahead and get started since it's on the hour. I wanted to, before getting into the slides and the demo, just show you like the community website for what I'm talking about today. And so this is categoricaldata.net. This hosts the open source software that I'll be talking about. And so as mentioned, it's more computational category theory than computational graph theory, but since, categories extend graphs, like there's a lot of technical overlap that we'll talk about today. Anyway, all the papers that you're going to see today are on here, and there's a lot of them. So there's like thousands of pages of stuff going back about 10 years ago. Those of you that know Sub, like Eswaran Subramanian, he is actually the driver of much of this stuff that, he was looking at things like graph theory in the 80s to do data integration, and then he found category theory, and that's actually how I met him. And so some of our original use cases in the tool you're going to see today have use cases from like the Department of Commerce in the US, and that was all driven by Sub. So anyway, yep, there's a ton of references here, screenshots. We have open source repo that Microsoft dumps a lot of code to. I'll talk about that today. And then of course we have our company. So anyway, with that in mind, I'll switch to the slides. Can everyone see a screen that says categorical databases? I'll assume that's a yes, unless somebody says no.
Yes.
All right. So, and I'll hope everybody saw like a web browser back there and not like a desktop. Okay. All right. So anyway, yes. So this is the usual like academic intro talk that we give. It is really designed more to get your appetite started so you can go to those papers that I just showed, right? Like some of them, they're 200 pages in a math journal, like we'll never be able to communicate all the intricacies during this talk. But I am like, as a startup, we're always trying to engage with as many people as we can, both in academia and industry. And so I hope this fosters a dialogue. Like I want people to email me after this talk and be like, where can we use our tool and that kind of thing. So anyway, onward and upward. Let's see how we make this thing go forward. Next page. All right, so what are we doing today? So the basic point of all of this, categorical databases stuff, that's one way to call it. Some people call it functorial data migration. We've heard it called the algebraic data model. There's, I guess, a lot of words for what we're going to talk about today, but the basic idea is to use category theory like directly to represent things like database schemas and databases, not kind of indirectly as you might get in languages like lambda calculus or even relational algebra, like trying to be direct as possible, and basically represent everything that data integration talks about: schemas, databases, schema mappings, queries, like with equations as much as possible. So a lot of times in the literature, we talk about algebraic data integration, algebraic data migration. And so you'll see the word algebraic a lot, but it's all category theory type of algebra under the hood. And the basic idea is that category theory, it's a branch of math that sort of moves theorems from one area of math to another, right? You can take a theorem from topology and use it to learn something about real analysis. And so like if it can do that, move theorems around, you'd think it could move like databases and queries around. Like what is a database if not like the kind of mathematics itself, but just like very simple compared to like topology or whatever. And so that was the basic idea, is that category theory should be good at doing this kind of thing because it's the kind of meta mathematics that mathematicians actually use for similar reasons. So anyway, there's an open source tool that we developed while at MIT, and then the company I'm at is trying to commercialize that. And so you can get the open source version at categoricaldata.net. It has all kinds of rewriting algorithms in it, con extensions left and right. It has automated theorem provers in it that are specialized for like the kinds of equations that come out of categories. It actually has like a dozen theorem provers in it. And so it's basically a resource for people doing computer algebra that arises from category theory. And then we take bits and pieces of that and try to like commercialize them. If you're a bank and you have a terabyte of data, like you're not going to run our in-memory open source Java version to do that. And so anyway, that's the company's focus. So the plan for today is I'll review just enough category theory to make sure everyone has like the words that they need. Talk about some of the theory underlying the tool, show the tool that we have, and then hopefully you guys can tell me where you want it to go. Like there's so much material here that I'm hoping you can like steer me towards directions that are interesting to you rather than just going through it. In the absence of anything, I'll start talking about how like the databases form simply type lambda calculi and start talking about functional programming in Haskell and like, crazy stuff like that. So anyway, hoping for more of a dialogue than a lecture, but how does that sound? Any questions so far?
Oh, it's good. Maybe let us know when you're at the point where you finished all the mandatory stuff, and then we can
Gotcha.
take it from there.
Cool.
Yeah?
All right. Onward and upward. So just a little bit more background. Like, as I said, we're going to talk about a data migration tool. It's going to use category theory rather than traditional theory. Why might you actually want to do that? Well, the idea is that in addition to giving you different data operations that you may not have seen before, like we've seen algorithms to move data around that relational database theorists, look familiar, but they've never actually defined them before. You also get a lot of static checking with category theory. Like when you're running around with presentations of algebraic objects, you can use theorem provers to like analyze them at compile time and whatnot. And so, sometimes we position this, we call the technology CQL because it sounds like SQL, and we try to position it as like a better way to do some of the things that SQL does. And then like we've interacted with some of the people in the community that you guys know doing case studies. Like when Chris Brown, somebody mentioned they know him when he was at the Stanford chemistry department. Like we worked with him to do some of this stuff. And now he's continued it over at the Topos Institute inside of Algebraic Julia. And like, we worked with DARPA and the people at Tinkerpop who were at Uber at the time. And so anyway, there's plenty of projects that are using this. And then we also like to think that it's, inspiration for projects like Algebraic Julia that are doing much of the same computational category theory, but like in a different way for different purpose. Like, they're doing epidemiology and stochastic categories and that kind of stuff. And we're doing more data. But anyway, questions here? All right. So hopefully this part here will go quick. I do want to review it though, because we're going to be blasting out words like category and functor kind of without really stopping to, like, we kind of need those words to be a baseline. And so what are categories and functors? Like, the good news is that to actually state like what functorial data migration is and how to use categories as schemas and so on, like you don't need too much category theory to define things. You need like a lot of it to actually prove things, but we can get away with just categories and functors for the most part. You know, for you guys, I guess you probably think of categories as gigantic infinitary graphs, or I don't know. There's, when we work with the graph community, sometimes they like to see a slightly different definition of category that makes it look more like a graph, and we use words like edges instead of morphisms and stuff like that. But anyway, I'm sure most people here know what categories are, and we can pause if they don't, but just to review. So what are they? You have a set of objects, or a collection of objects, and a collection of arrows in a category. So two sets of data. Objects of a category C are written obc. Between any two pairs of objects, you have a set of morphisms, just a set of things. We call them morphisms. Sometimes we call them arrows. Given any object, you have a distinguished identity morphism written identity underscore the object that the identity is at. We'll often omit that underscore when it's clear from the context. And then for any three objects that you can arrange the arrows of tip to tail, like in a graph where the target of one is the source of the other, you have an associative composition function for which the identity arrows are its unit or neutral element, right? If you compose identity with F, you just get F back no matter which side you're on. And then you have associativity of the composition operation here. People might be used to seeing a semicolon instead of a circle here for like the other order of composition, like you see both of them. But anyway, what's a category that most people are probably familiar with? There's the category set. We'll see it a lot in this talk. The objects there are all the sets in, say, ZFC set theory, and then the morphisms are all of the functions between them that you can write in set theory, like up to provable equality. There's the category Haskell. It has types of objects. Its morphisms are programs, and pretty much everything in the universe turns into a category. We'll see that database schemas do too. But let me pause there. Everybody familiar with the notion of a category? All right. So what else do we need? Oh, question. Oh, okay, cool.
Yes, so
there's a question.
If we don't answer, the default will be yes to this question.
Gotcha. Okay, cool. Onward then. So the other thing we'll need we'll need a couple things, functors and natural transformations. But what is a morphism of categories? So, you know, if you have one of these giant infinitary graphs that are, you know, edge closed, for example, what would a morphism of them be? So if you have a category C, category D, a functor between them, it's a function that takes the objects in the source category to the objects in the target category, and then a function that takes the morphisms in the source category to morphisms in the target category, like assuming their objects get moved along according to the function also. And so basically a structure preserving map between categories is called a functor, and they obey exactly the algebraic identities that you would expect them to. You know, one of the overall themes of this talk is that when you use category theory, at least for data integration, like there's sort of no choice in like how you define things. Or, you know, like the notion of a functor has to be defined this way. The notion of you know, database schema has to be defined the way that it is. And so that's like, it provides a lot of guidance, we might say. For us, our functors will be mappings between database schemas, where each database schema is the category. It's kind of foreshadowing, but anyway, some example functors that people might know about. So if we're in the category of sets that I talked about before, there's actually a couple different power set functors that do different things on the arrows in set, but the basic idea is that the operation of this functor is to take each set to its power set. There's another functor in the category of Haskell programs called the list functor. It takes every type T to the type of lists of that thing. And, you know, since there's categories everywhere, there's functors everywhere. And there's also a notion of a map between functors that we'll see later, but I'm going to try to not define here because we don't really need the math at that point. But anyway, all right, let's continue along. Oops. There we go. So this is the 1-page slide and summary of how all this stuff works. And so I'll try to give an intuition about the diagram and then talk about its meaning in terms of category theory. So one way you can think about this is we're using category theory as a denotational semantics for schemas and data that look like what you're seeing on the screen here. Like that's one way to think about it. And then there's other semantics possible besides the categorical one. But anyway, what are you seeing on the screen here? So we've got a directed labeled multigraph up at the top. The nodes are meant to be names of tables in a business database. So employees, departments, string is kind of a weird table, but SQL, you have varchar 255. That is, if only theoretically, a gigantic table full of strings. And so also on here, you have directed labeled edges between the nodes, things like works or secretary. And the idea here is that the edges represent what are called foreign key relationships, that every employee should also have a department that they work in. And that department that they work in should also have a secretary that is also an employee. And so, like you see, there's this little cycle in this graph. Here's another cycle called manager. This is, you might argue at the top of a company, maybe you have a self-manager called the CEO or something. But like, anyway, the point here is that we're trying to write down database schemas. And for many decades, directed labeled multigraphs have been used for exactly that purpose. Sometimes these graphs are given meanings in like relations, sometimes in functions, sometimes in like stochastic relations where you have a like confidence interval associated with each data point. Like, the sky's the limit. What category theory is bringing here, at least for the purposes of this talk, is the idea that if you equip the schema graph with a collection of equations, like between the paths in the graph, then what you've actually specified is a presentation of a category. And now your schemas are categories. And so the insight that David Spivak had was that the like generators and relations that you might write here, like as a mathematician, you might say like, all right, I want the path starting an employee that finds the managers and then finds where they work in to be equal to the path that just finds like where those employees work in. Like that expresses a data integrity constraint, a business rule that says the managers actually work in the same departments that they are the managers of. Right, your math manager works in math. He doesn't work in corporate or something. Ditto here, this one at the bottom is saying that every secretary works in the department that they're the secretary of. You don't have any secretaries working for math that are the secretary for computer science. And so like the insight in the categorical data model is, category presentations, directed labeled multigraphs with equations between paths. Those happen to be categories already. And so we can read graphs at the top like as little categories. We take the category formed by all the paths through the graph. The zero length paths are the identities. And then the composition operation between paths is like, do one path, then the other. And then you like consider all of the paths through this graph up to provable equality under the equations that you have. So I'll pause here. I'm getting a little ahead of myself, like how you turn a presentation of a category into a category, but that's like kind of where this is going, that we're going to see schemas as categories and the data on them as functors from that category into the category of sets. And then we're going to see how much guidance category theory gives us to like do data migration and how that's different from relational algebra and graph operations and so on and so forth. So I'll pause here, questions, comments, and then I'll talk about the data underneath. But I just want to make sure this top diagram makes sense to people, at least the intuition.
I think that's very clear. Thanks.
Okay, so then at the bottom here, we have a database on this schema. And so, you walk into your average Fortune 50 company, they're probably more used to thinking in terms of individual tables than like entire databases at a time. But what category theory is telling you is that like the unit of study should really be an entire database. And what those are functors from the category you have at the top into the category of sets. So what do I mean by that? What I mean is that for each node up here, you need to give a table. So here's your employee table, here's your department table, here's your string table. This one's a little funny because it's so large. And then for every edge, or rather for every path through this graph, you have to be able to pick off a function. And so what those functions are, they're going to be functions from rows to rows. And so like I'm playing a little fast and loose here because one of the interesting things in category theory is that you like can't distinguish sets by their elements, only by their structure. That like, you know, any 3-element set is sort of the same thing as any other 3-element set. That like the way this works conceptually is that every table you think has or you can, one of the ways to do this is say, all right, these tables, they each have an ID column that like lets me refer to that row. And so that I can give like the meaning of this works in function, like as a row in a table. Right, this works in function takes department Q10, or sorry, takes employee 101 and maps it into department Q10. Like that is the department that employee 101, whose name is Al Aiken, like actually works in. And so, yeah, I guess to make a long story short, like if you want to write down a set valued functor from the category up at the top, then the way you would do it is for each object, you would write a table. You would give that table like a primary key column called ID so that you can like talk about what are the individual rows in it without having to write down like, you know, the whole row itself. And then for the columns, you just like fill in the data that you actually want, like according to the rules. So if we like look at this rule set, we find that every secretary really does work in the same department that they're the secretary for. Like these equations are satisfied by these tables down below. Like that's what it means to have a set valued functor, basically. That there's no way to even define a database that doesn't obey these data integrity constraints because they're built in to like the mathematical definition of schema. So anyway, that was a bit of a ramble, but hopefully people are getting this idea that associated to the schema, if you want to have a database, what you need is a table for each node. You need like a function for each path. You can read those off these tables that have one column like per edge in your graph in a kind of inductive fashion. Like if I wanted to get from employee back to employee through works and secretary, I'd like come down here to the works column. I come over here to the department table. I'd look at the secretaries. Now I'm back in the employee column and then like everything works out. So anyway, how does the data look? Do people believe that you can put databases on schemas that look like this and that these things might be set valued functors? Like we'll get into a bunch of math on the next slide, but I want to kind of check the intuition first. Everything good?
Yeah.
All right. So, or I guess we'll get into the math after a little detour into the code. So I'm going to show later like a tool that does all of this stuff, and to actually do it, that's to like solve the word problem for categories. And so it has theorem provers and so on and so forth. But anyway, if you're actually going to type this thing, sorry.
Do we have not partial maps somewhere?
These are, right, you're correct to observe that these are not partial maps. Like these are total functions here. And that if you want a partial map, then you have to basically model that as a span. Like you create another dot and then two functions and you represent like the relation as a pair of functions. This is at least for us, by targeting the category of sets rather than say the category of relations. Everything in here is a total function, which kind of makes this a generative data modeling tool. Like you're presenting data and schema here, and the fact that everything's a total function like generates additional secretaries and managers and so on and so forth. But yes, this is total functions, and so you need to like add extra arrows and stuff to model things like relations. Good question.
But then I have a follow-up question on that maybe. When you turn them into spans, then they all get multi-valued certainly. And in company database, you often have a lot of like nullable columns. So
yeah, so there's a few answers to that. So like,
okay.
Sure, when you encode things that way, like they turn into multi-relations. But on the other hand, SQL is based on multi-relations. Like when you actually work on large data sets, you're forced to use multi-relations because it's intractable to like remove the duplicates. And so that's why SQL works that way. So like to capture SQL semantics, it's actually good. Like the fact that you're in multi-relations helps you. What else can I say about that? Oh, and the null values. So the way SQL works is, it has, in addition to like this idea that you might have a missing value in your database that would be determined later, there's also this thing that SQL has just called the null value. Like there's a special string called null, and there's a special integer called null, and there's a special date called null. And like everything in SQL, like it uses a 3-valued logic. Actually, they don't even specify which logic. There's like a couple of different logics that are compatible with how SQL works, and they differ on like the meaning of logical symbols that SQL doesn't give you. And so, yeah, there's this separate question of if you're trying to model SQL specifically with its bizarre like null semantics, where you have basically what you might call lifted types rather than what we'll see later are called labeled nulls, then like we have to do a little more work in this model. Like there's nothing, this model doesn't represent that. And so one of the innovations that David Spivak had and that we had to implement in the tool was like how to do things like that. Or what do you do when you want to say something like, the age of the managers +1 should be the sum of the employee ages -5, or like there are, one of the questions we're not answering on this slide is what do you do when you need more modeling power, like things like SQL nulls, or you want to talk about relationships that involve addition or string concatenation, and so that's where category theory starts to shine, because you can say, all right, well, I want to have like a product category with attributes instead of just a plain category. And then like you start to pick all that stuff up in the math. And so anyway, this is a starting point. Like all the work we did with David Spivak in the company is like how to bring this in line in the real world so that like we can run it at a bank rather than, on paper. But yes, that's a good question. SQL it has its own weird data model going on, and it's like not this nice one, right? You have things like the null string equal the null string. The answer is not yes. And you have to like be very pedantic when you go to model SQL's 3-valued logic. We like relational algebra much better, frankly. There's easier ways to connect relational algebra than SQL. But anyway, that was a rant. Did that answer your question? I hope so.
Yes.
Okay. All right. So right, and then there it is in the tool. So yeah, what's the math behind what I just said? So I tried to say this like with words, but let's put it on the screen, because we're getting to the point where like to define things like rewriting that we're going to do and whatnot, like we're going to have to start getting into the math to say what it is. So right, what did I just say on the previous screen, but more formally? So we have a directed labeled multigraph with a system of path equations. It's called S. We're trying to build a category called church brackets S. Like if you're into type theory, I'm sure you've seen these brackets a lot. They're just what people use to write the meaning of a syntactic object. So what are the objects of this category? It's just the nodes in the graph. That's easy. What are the arrows in it? Well, the arrows from X to Y in this category are the set of finite paths in the graph, but they're equivalence classes of finite paths. They're equivalence classes according to those equations that I wrote down, things like every manager works in the department they're the manager of. And so this is where all the decidability comes in, because if you have just a system of equations like we have, there is no algorithm that can say whether or not two paths are equivalent under that system of equations. And so like, notice immediately that when we're dealing with categories rather than graphs, and we're dealing with presentations of them, like, we have group theory running around, like you can write groups in that syntax. And so the word problem for groups is actually lurking in here if we're trying to do path equivalence. And like we kind of, categories are so expressive that like on this slide right here, like we're hitting undecidable problems innately. And so, we always like to say that applied category theory is just computer algebra. And this is kind of the reason that if you're dealing with presentations of categories, which you probably will be, because most of the categories of interest are infinite, then you have to do path equivalence to like work with them, or decide word problems to work with them on a computer. So anyway, if you look in the literature, this is called the word problem. It's like finding the equivalent of two representatives in a system of equations. There's many other phrases for this problem, but they're all like kind of the same, or you get the same undecidability, like, kind of no matter where you look in the literature, but the word problem is a good place to start. But anyway, bearing that in mind, what does a functor look like in this syntactic thing? So if we have two directed label multigraphs, say S and T, then those induce a functor from the category of S to the category of T. And the way you define it in a syntax is an equation preserving functions. So you write down a mapping of nodes of one graph to nodes of the other. And since it's like one node per table, you're going to have a finite number of tables. That's kind of a nice thing in this databases model world, only finite number of tables usually. And then what you have to do is write a function that like generates the action on the arrows. So for every edge, every generating morphism in S, you write down a path. So this is a little different than in graph theory where you might map edge to edge. Here we have to map edge to path. And it really does have to be edge to path. If you try to do edge to edge, you lose expressive power. And so applied category theorists will call this a derived signature morphism as opposed to just a signature morphism. But anyway, the point is I might have to map an edge like manager to a path like, uncle's brother's mother's former roommate or something. A joke from a movie Spaceballs. But anyway, so that's how we write down mappings between schemas, and those turn into functors. Like the fact that the assignment you write has to be equation preserving, which you have to check like with an automated theorem prover, is exactly the condition that guarantees that you have a functor between categories and not just some arbitrary assignment. So anyway, we'll see examples of maps between categories later. Like the reason to define all of this is that we're going to use functors as a way to move data around, like as a way to change the schema that a database is on, as a way to query databases. And like, that's why we're setting all this up. Like really, we're asking like, can we use functors as queries and things like that sort of directly is the math question. But just to be fully precise, let me define the other stuff too. So what's a database instance? Like that's just a special kind of functor. So it's a functor out of your schema into set. And so basically, what does that mean when you unroll it? Well, for each node in your schema, you have a table. For each edge, like generating edge in your schema, you have a column. And like when you look at those tables, like they're supposed to satisfy the equations you wrote down. Like we've already seen this one kind of informally. A mapping, I guess I'll conclude by saying that like the notion of natural transformation in category theory, it comes up here too, like a mapping between functors, what we would call a natural transformation in category theory, like when they're between set valued functors, you get the same notion of database homomorphism that database theorists use. And so I guess what I'm saying here is that this setup recovers much of database theory, including definitions like database homomorphism that were invented like before category theory really existed. Like this reduces to the same kind of theory that database theorists are already doing in like, I guess, a cosmic coincidence or the sign of God's love or something. Anyway, I'll pause here briefly so that people can see this on the screen, and then we can dive into the like technical specifics of like rewriting and stuff like that. So let's do a example here of a schema mapping. And, this is not too different than what we see in practice. Like we've seen many banks write, things that look like this. And, it seems prosaic, but like, sometimes really all they are doing is figuring out like, which loan bucket to some big company go in, and like they really have data scientists write little functors like this and move data around. So it's not as trivial as it may seem, but this example is a bit contrived just so that we can like see the corners of the math where things like all the fun stuff happens. So anyway, let's say we have two schemas, S and T. So this one will be S on the left with the 4 nodes, and this one will be T on the right with the 3 nodes. F goes from left to right. I said we had to provide a mapping from nodes to nodes. So that's like string goes to string, it goes to int, N1 goes to N, N2 goes to N. So this is like where all the action is N1 and N2. I said we had to give a mapping from edges to paths. So name goes to name, salary to salary, age to age. This path F, or this edge F, where do we send it? We send it to the 0 length path on N. So that's this little thing down here. And so, bam, this is what our CQL tool would call a schema mapping. This kind of thing is generated from like a lot of like SQL-based tools would generate something like this. I guess the point I wanted to make is that this is defining a functor. And since this is defining a functor, like now we can do things like move data from one schema to another, or like take other functors and do things to combine it with this one, or like we can start doing formal stuff. So anyway, questions here on our example functor. Like we'll see other ones later, but like if this one doesn't make sense, then we should pause. But I'm guessing this is pretty easy. Like this is basically a graph homomorphism with the caveat that edges go to paths rather than edges. So like this action of F here, like I don't think this would be a graph homomorphism, like stop me if I'm wrong, but I think like since you have to send F here to a path rather than an edge, I don't think this would be a homomorphism of graphs, but we consider it a homomorphism of categories.
Ryan, quick question. Is then, so to speak, the burden for the user or the tool to prove that since you are doing something non-trivial with this path, which was between N1 and N2, to show that still sort of the equations would be valid? Is there some sort of proving step necessary, or how do you do this? Yeah.
That is correct. And now I can even break out the tool here. Let's see which demo. This is a little, here we go. Wasn't quite meaning to get into the demo just yet, but there's, just to give you an idea about the ecosystem, like for us, our policy has always been, we're going to switch back. Oops. There we go. Like we want users to never have to prove anything. Like for us, you can't have a data analyst at a major bank proving that their functor is correct. Like they don't know what proofs are. And so like our automated theorem provers are doing this checking here. And I'm going to show the tool and how it does that. Other people in the community, the applied category theory community, like the folks at Algebraic Julia, for example, they take the opposite approach. Their users are like scientists, and they have really complicated functors that like an automated theorem prover probably wouldn't be able to do automatically. And so they have people like, you know, swear that what they wrote down is a functor, or like they're thinking now about letting people write proofs in other languages and put them in. But like, yes, like this has to be checked that this is actually a functor. And when you have arbitrary graphs on the left and right with arbitrary equations, that's an undecidable problem. And like there's an example with like 6 nodes and 8 equations that like no computer can solve. And like, yeah, it hits you right at the beginning. And so to evidence that, I was going to bring the tool up. So could everyone see the CQL IDE? And I'll make this one a bit bigger too. It should say schema privacy policy at the top, and then schema people below it. Yep. Okay, cool. So this, as you can imagine, like the application here is in like securing information and privacy policies. But what I'm going to show you is how the theorem prover is working. And it's not even really going to be theorem proving. It's going to be more like functoriality checking. But I just wanted you to see it in the tool, how it says like, yes, that's correct, or no, it's not. So anyway, like, yeah, this is the walking arrow category, they would call it, 2 objects and just an arrow between them. This one is the loop category, 1 object with a loop on it. So like the category this denotes is infinite. You know, you do need like graphs with loops in them as schemas in practice. Like you can't get away with, sometimes people think, oh, we'll just have directed graphs, but like, no, in practice, foreign keys become cyclic. Anyway, I guess the point of all of this is that let's write some functors with the tool called schema mapping. So if we're doing a functor from people to privacy policy, we can map person to private and then mother to the identity path. Similarly, you can watch person to public and mother to the identity path. Like if we push the run button, hopefully you see a screen here that just like a pop-up happened and like there's some stuff, like nothing went wrong. But if we try to write an assignment that's not a functor, like this thing here called M1, where we take person to public and mother to like the arrow rather than the identity, like this is no longer a functor. And so here, like you can figure that out based on like, there are no equations to check. So it's kind of an easy thing. But the point is, if, you know, if this were failing because of the equations, like you get the same error. Like this tool will not let you write down things that are not functorial. It won't let you run them. It'll like stop you with a squiggly line before anything happens. And so one of the value props for this is like, you know, you can check SQL code you already have, you write it down in functorial form, and then like we have a product based on that. Or you could use this before running algebraic Julia to check functors and hook the systems together. Or like there's a lot of applications of this kind of static checking, but yeah, it's all theorem provers under the hood to make it happen. And so anyway, this is like, here's another one that doesn't work. Like you can't, like basically you always have to map the self loop to an identity. You can't map it to like the arrow, like the functoriality doesn't work. So anyway, yeah, questions there?
Could you map it to another self loop?
Almost certainly. Yeah, so why don't we try that? So if we put in like F going from private to private, or I don't know, like I said that flippantly, but it's actually often very hard to predict these things. Like you actually have to run the theorem prover to figure out whether or not it works or not. Like even in coming up with examples for slides, like I often find myself having to run the tool on like little examples because I can't imagine what it's going to do in my head. But anyway, yeah, the question was, if we put this thing to F, does that work? Yes. But I guess that's kind of expected. Like there's no interaction here between like the self loop that I just added and like the old thing called classify. But like in practice, what people actually spend their time doing in this tool is like looking at these arrows and being like, oh, that's wrong. How do I fix it? And I guess just jumping ahead a little bit, if you've heard of something called a profunctor, it's like a generalization of functors, but it gives you a syntax that looks a lot like SQL syntax does. And so like usually the example we give isn't based on functors, it's based on profunctors, and profunctors look like SQL code. And so we give this cool little demo where you're writing like a collection of SQL queries and you forget a condition in one of the where clauses, like down here. And then all of a sudden, like your query breaks. And then, you know, it's like static checking for SQL. So anyway, sorry, I couldn't resist this one other. I guess the point here is that the theorem proving isn't just for functors. It's like for every artifact that you have in category theory, there's always some kind of functoriality condition, and that those are always checked. And that as a result of always checking them, you can use this tool to do things like analyze SQL code and lots of other cool stuff. But anyway, back to the slides. So yes. All right. What do we do with all that stuff I just mentioned? And why do we have these t-shirts with the cool little logo? This is the slide right here. Like, you know, how can you do all of database theory using category theory based on one definition? Like it's all here, and it has to do with these things called adjoints. So suppose you have a schema mapping F going from S to T. So let's write it down like this. Bam, there's F from S to T. And you have some database instance on your target schema. That'd be a set valued functor. So let's call it I. Database people like to use I and J for databases, and like F and M and G for functors. Anyway, the point is, using category theory, you can compose these things, right? That's kind of the definition of what the category is so this diagram here is in, we'd call the category of co-presheaves, or no, sorry, it's a category of categories. Right, here's set appearing as an object. But anyway, the point here is that you can compose your schema mapping and your database. And because they're both functors, you know, to database theorists, this is bizarre. Like you took a schema mapping and composed it with a database. Like one's a set of tables and the other is like an assignment. How the hell did you do that? But like mathematically, it all works out. And what you find when you do this is the composed arrow, it goes from S into set. And so you basically, if I give you a functor from T to set in a schema mapping from S to T, like it's easy to give you back a functor from S to set. Like you get like for free, basically this ability to change the schema that a set valued functor is on. And I'll like go into detail about how you would do that later. Right? What's coming up next is examples of these. But the point I'm trying to make here is that category theory, it gives you a way, given a functor, to transform databases in the opposite direction. So if your functor goes from S to T, you have a way to take T database instances to S database instances. Like it's reverse direction. That's simple. It's defined using composition. The magic happens because mathematics proves that this operation, there we go. It has partners. It has things that do not invert it. Like you can't like undo projecting away data and dropping a column, but you can like freely add new data and work out the consequences according to the equations in your schema and whatnot. And so basically what David Spivak and others proved is that like, this operation here called delta, precomposition with your schema mapping, like that always exists, but moreover, these partners always exist. And so the algorithms to actually calculate these things are very intricate and hard to write down, but the definitions of what they're doing can be written in a single line. Like the way that you define, this pi function, it's called the right adjoint to this delta f thing. Like it's defined as the unique operation such that when you examine all of the morphisms from, delta f of some database to some database J, God damn it, it's the same as, some one-to-one correspondence with all the database homomorphisms on the schema T between like the unprojected input and the pi on your other thing. Like I don't expect people to understand the notion of adjoint here. I guess what I'm saying is that like what category theory is doing is telling you what projection is. And then it's saying like, now that you understand what projection is, things like relational join are recovered as what's called the right adjoint to projection. And things like what are called relational chase algorithms, these are sort of things where you're doing unions and then merging of data. Those are recovered by this left adjoint. And that they're like, because they're defined that way, they all work together well. Like you can do things like round trip data, and like you can like analyze mathematically like information loss and so on and so forth. So anyway, the rest of this talk is basically like working out what these data operations are, giving examples, showing how they're useful in practice, and then how they differ from like their relational counterparts. Like it's like join this thing, except it's working on multi-sets of bags and, blah, blah, blah. And this one is a little less, this one you can't do with relational algebra. You'd end up with like a recursive query into like craziness and stuff like that. So anyway, but this is where like my background comes from and like all of that. So I'll pause here. Have people heard the word adjoint before, just out of curiosity?
Yeah, I think we're familiar with that. Maybe.
Yeah.
Okay, good. That helps.
Related question. So, if the adjunction here is the main thing you're interested in, as you probably know, this works for more than equations. So you could at least use conditional equations. More generally, from a sort of categorical or sketch terminology point of view, these would be, finite limit sketches, isn't it? Where you can define.
Yeah, let me speak to that. So you can and often do need things beyond equations. Like if you wanted to write down, some set of columns is a primary key, like you'd need more than equations to do that. So one of the slides I have later is what do you do when you need to go beyond equational logic? I will say this though, I believe that equational logic is the only logic for which you get both pi and sigma at the same time. That in any logic, you get delta and sigma, like those always exist, even for finite limit theories and so on and so forth. But if you want all three of these at once, that you need to be in equational logic. So I don't believe you have the right adjoints, for example, in a finite limit sketch, nor would you expect it. Like it's kind of like as you get more modeling strength, you would expect less ability to functorially move data around. So anyway.
Yeah, you're right. So you get the left adjoint, but not the right one if you go.
Right.
Okay.
And in
thank
practice,
you.
the tool just lets you mix and match, right? If you need non-equational constraints, you just write them down, and then the tool is like, all right, but we're not going to be able to preserve these things. And the point is not that this is the most awesome thing there is, just that there's always an engineering trade-off between how expressive and how much reasoning you can do, and we want to help people find the right trade-off. So much data modeling is like, what's the best data model? And that's so weird, right? It's like asking what's the best coordinate system. Like, the idea is they're all kind of different, and we want to use math to relate them as opposed to pick the best one. But yes, that's a good question. And like a lot of the previous work on things like finite limit sketches, they weren't so much about functorial data migration as like other things. Like this is now we're getting into David Spivak's part, which is noticing that these operations exist. Like some of the original work by Rob Rosebrug and Mike Johnson, and like from the 90s, they wrote a paper called A Database of Categories. Like they found this sigma thing, but they didn't find its adjoint partner, for example. And so that's kind of David's specific, the data migration aspect as opposed to the sketch part. Like everything here is basically a finite limit sketch, like sort of trivially, as you've seen. Anyway, let's move on and upwards since, sorry, question here. Got it. Okay. So yeah, I'll give some examples and then we can show the tool more. These examples are contrived. And then I guess the point for you guys is that the way these are implemented uses rewriting under the hood. Like I'm going to show you all things that operate on model, but the way that the algorithms are defined is you like take a model, turn it into equational theory, do substitution or whatever on the equational theory, and then build like an initial model using a decision procedure, and off you go. So the actual like implementations of these things use rewriting under the hood. But since we're talking about databases, which are models, like I'm going to show like less of the rewriting. It's actually, so we wrote a paper called Algebraic Data Integration that has like a syntactic side and a semantic side, and it shows like substitution is sigma here and like composition is delta here, and it tries to relate them. And so I guess there's more rewriting relationship here than they're coming off in the talk, just because I guess the rewriting happens more as an implementation technique than like a semantic one. But anyway, I'm rambling, but let's get back to the example here. So suppose you have a schema mapping F that looks like this. I've removed the edge F here in the source schema to make the example degenerate, just to show the differences between like sigma, delta, and pi, that they come out most when you have kind of edge cases in your data. Like this is kind of a weird database system to have, but it's like totally well defined. So anyway, if your functor goes from left to right, it's the same functor as before. N1 and N2 both go to N. There's no edge between them to map anymore. The induced data transformation, like pre-composition with F, it takes this thing on the right, this one table, and it breaks it up into two tables on the left. How does it do it? Well, the table on the left, there has to have two tables, like we know that according to schema. So we ask ourselves, all right, how would I answer a question against N1? Like what rows would I put in here? Well, I say, what would I do? Well, first I'd ask F where N1 goes. And so I would go over here to the N data, and I would look at like where salary goes, and it gets mapped to salary. And then I'd like move the salary over. Like I basically, the way you populate the N1 and the N2 data is you look at where the functor sends it, and then you use that as your answer. And so anyway, in this example, like here's how you like use a functor to split up a table. Like if you start with N and you want to split up into two tables, N1 and N2, you create a new schema that has like two tables in it, and you map into your data. And then you use this delta operation to move reverse to the functor and split it up. So people that use SQL they may be familiar with from clauses and how the from clauses have what are called as clauses. And like you're actually like this little reversal, like you point something one way and then the data moves the opposite way. Like that actually happens in languages like SQL, but you typically don't realize you're doing it because it's all encoded in what are called the as clauses. But anyway, this is how you would do a projection. Like this in SQL, you'd say like, select N as N1 and select N as N2, and that kind of thing. But anyway, like, yeah, here's the first operation. This based in totally on precomposing with this functor F, the set valued functor you already have. I'll pause here. This is usually the first place where people start having to like kind of, or where the intuition where you start having to use intuition as opposed to like calculating things. But and I'll show example of this also where we put the edge back to get a better intuition. But questions here so far?
No, I think that's clear enough. Thanks.
Cool, right? And then I claim, because once you've seen this, the rest is just math, right? You should be able to replicate the CQL tool and all the 8,000 pages just based on this. I'm joking, but it's actually like that's one of the cool things about this is like how much follows from just basic category theory here. Anyway, let's look at the other operations in this degenerate context. So same schema mapping as before. We don't have this N1, N2 edge, so it's kind of contrived. But what does the product operation do? It moves data from left to right in a product-y kind of way. So you can kind of see already I'm playing a little fast and loose with like the actual data that are in these rows, like A, B, C, D, E, F. It's a bit of a dirty secret that like, with category theory, you can't really distinguish isomorphic sets. And so like the tool actually has to pick like which identifiers to use and stuff like that. But like the real point here is that you have 3 things in, 3 times 3 is 9, here are 9 rows, and they all have like the data that you would expect in it. I often tell this story, the first implementation of left con extensions we did with David Spivak, like all the data dropped and it was replaced with like made up identifiers. And I took it back to David and he's like, oh yeah, that's right. Correct up to isomorphism. It's like, dude, we have to keep people's names like Alex and Bob and Sue around, or it's like not a database. It's like, oh, all right, well, we have more work to do. But anyway, side note. Yeah, questions here on this product operation?
Which joint was that now?
This one would be a join if we had an arrow from N1 to N2. There's nothing actually to join on here.
Sorry, which adjoint would that be?
This is the right adjoint.
The right adjoint, okay.
And this is the one that disappears when you have like finite limits and stuff. Like in general, you won't be able to preserve those products through these kinds of operations. Yeah. Okay. And then the other one coming up next, the left adjoint. So this one, rather than multiplying and filter, it Eugens creates new values. So this is where this will look weird to someone used to SQL, because this is generative. Like the database will have values in it that do not exist in the source. And so like that, this is what's called not domain independent in a database theory language. Like we've had to invent new values here, null 1, null 2, null 3, to indicate that they're different from each other. Like in SQL, you might get the same null value in each of these, and like that would be wrong. And like, anyway, you need more than relational algebra to like express what this left adjoint is doing. And that's why there are tools like Informatica and the IBM high-level integration language. And like, this is why people use ETL tools rather than like relational algebra to do this kind of thing, is because you actually need to do like this kind of semantics where you fill in missing values. Here, there's the missing values just sit there. Oftentimes, like the equations you have in your presentations will force them to take specific things like, oh, this null 4 is actually Charlie because I know that from some other way. But anyway, I guess the point here is that the semantics here is dual to what join was doing. So join producted things and then filtered them. This is going to union tables together so that now they have null values in them. And then it's going to start squishing rows together to remove the null values. And so in this example, there's not any squishing. Like we're missing an edge here that would allow us to do the squishing. And so like the missing values stay there. But anyway, it's 3 things in plus 3 things in equals 6 things out. And so you can kind of see the sum or the additive nature of this. And I'll come back. The next thing we're going to see is what happens with the edge in here, and you're going to be pleasantly surprised. But I'll pause here for questions on this one. This is the left adjoint and the one that you can't do with relational algebra alone.
Okay, yeah, I think that's good.
Okay, cool. All right. I guess as a side note, yeah, the interplay between what's called domain independence and relational algebra and category theory is kind of an interesting one, because they, it's a philosophical question. Like should you be able to return values from a query that don't appear in your input database? Like back in the day, logicians used that as the definition of what a database was. And so this is like kind of an unnatural thing from that point of view. But at the same time, from another point of view, you should be doing that. And so it's, I don't know, a lot of our papers touch on that kind of thing. Okay, so before showing like what that example looks like with the foreign key in it, that makes everything like sort of obvious, I want to show what you can do even with that degenerate example and like why it matters that these operations are defined the way they are. So because sigma and delta are defined as the adjoints to precomposition with F, the delta operation, or sorry, sigma and pi, like sigma is the left adjoint, pi is the right adjoint. Anyway, the point of this is that means when you do these operations like in sequence, you still can relate them to each other. So we call this round tripping, and this is something that you can't do in SQL, and like we have products based on this and so on and so forth. So if you start with your two databases like this and you sigma them, like I said, to like you get these missing values. Now let's delta them back to where they started from. Like let's split them up again. When you do that, your null values, like they propagate, and even our IDs have changed. Like I'm playing fast and loose with the like set Zerupti isomorphism type of stuff. But the point is, like these databases, they're not equal. Like adjoints don't invert things. That's too strong. But there's always a unique way to map from where you started to where you're going, right? Alice, Bob, and Sue, like they recur in the target database. And so basically, like what this is telling you is that you can quantify information change, like by doing your operation, doing its adjoint partner, and then using the unit or the co-unit of the adjunction. Like table by table, that function will be injective or surjective or bijective, and you can like, that quantifies the information change through your functor. And so like, you know, when we work for the Defense Department, we say things like, yep, you're losing a bunch of data on this one, or you're creating new stuff in this one. And, you know, they seem to like it. So anyway, you get more stuff out of categorical algebra than you do relational algebra, such as this kind of round tripping with the unit of the adjunction. I'll pause here. Questions on this round trip?
No, I think that's clear.
Okay, cool. Then I'll try to finish up the content here, show the tool a little bit, and then get you guys interested. Like, as you can tell, the point of this talk is like, you know, this is like the first 30 pages of the 3,000 that are on the website. So it's more about getting you guys interested for more dialogue than reaching the end of the material. So anyway, here is what happens when you have a foreign key. And so as you might expect, being based on category theory, like everything just sort of works the way you expect it to, like automatically in a situation. Like, you know, we'd expect there to be a foreign key like this in this example, right? That says like, here's Alice, and it actually connects her to the table that has her age, right? Like it's weird that there wasn't a foreign key to begin with. What's fascinating is that when you have this foreign key on the examples we've been doing, like they all do the same thing. Like pi and sigma, they give you the same answer. They both do a join. Like one does it by producting and filtering, and the other does it by unioning and swishing, but they both get you to the same place. It's saying that like the way your data moves is much more a function of what your schemas are than like what the mapping you give is. And so like, yeah, for, you know, mathematical reasons, the left and right adjoint actually behave the same way on this example, and they both do exactly what you would expect, like merge the tables along the foreign key. And similarly, the delta operation, like how does it move from right to left? It splits them up, but populates the foreign key. And so like, anyway, 9 times out of 10, when your schemas are correct, like you can get away with using very simple functors, and it often the choice of which adjoint you use doesn't even matter because they both do the same thing. But anyway, so that's, yeah, pleasant surprise on this stuff. I'll pause here for questions, and I'll try to do like a lightning tour of the rest of the stuff so that you can see where this goes, and then wrap up.
Is it possible to say under which condition this happens? I mean, it looks like the schema is sort of connected now, where it was slightly disconnected earlier because you couldn't reach.
Right. This is all worked out in details in those 3,000 pages of math. Like, you know, I think Patrick Schultz has an answer to that involves by category equipment things and, you know, all kinds of craziness to answer that. But yes, for us, often we're interested in like what conditions do you put on a functor statically to guarantee that when you run sigma, that the merge doesn't do things like try to merge Alice with Bob. Like that'd be for us a contradiction, whereas like category theory might proceed, or like we have a lot of results that relate the static form of the functor to the behavior of these induced data transformations. Good question. Yeah. Are there others?
In sort of the nearest thing I can imagine is, Uwe is more of an expert in this than I am. So in morphisms between algebraic specifications, so equational specifications, you have notions of sort of conservative extensions and things like that.
Oh God, yeah.
I wonder whether that's a related question there, because it also means that you're not identifying data that wasn't.
Yes,
that
is exactly you caught me when I said contradiction. That's exactly what I meant. So, in fact, we can even. Let's not get too much into the tool. So the yes. So what actually happens here is that you are building, like sigma builds a new algebraic theory. It basically builds it by substitution. Like you take these tables, they're a model of a theory. You turn them into like what's called a saturated system of equations on that theory. Like you basically list the model out as a huge set of equations. You substitute along your functor, like in a syntax kind of sense, that gives you a new theory in a different signature. And then you take its initial model, and that tells you what tables to get. Like that's how sigma works operationally. Now, when you do that, you may find that you prove more things about Alice and Bob than the input database did. Like maybe the input database said Alice and Bob are not equal, and your output says that Alice and Bob are equal. And so like now we have a non-conservative extension. The theory that sigma gave to us is a non-conservative extension of the theory that it started with. And so that is for us what I call a contradiction. So, but it happens in arbitrary logics. Like the RDF people worry about this. They have algorithms that check it, that run in like double exponential time. And it's non-conservativity is what we're actually worried about. And that is a very hard condition to check. It's beyond undecidable. It's like co-undecidable or something like that, or like undecidable on top of undecidable. Or, but yes, it does turn into a conservativity check. And if you guys happen to know methods to do conservativity checking, especially algorithms, like I would love to have them, because that, unlike theorem provers that we have like lots of, there's only a handful of algorithms that can check whether or not something's a conservative extension or not. I mean, they're all like heuristics, of course, but like that is a huge open problem here. And I would like to see more work done on it. Conservative extension checking. Yeah. Good observation. Very, very, very subtle and technical, but yeah, that,
all right.
That hits us.
I wanted to see if I had the right intuition there. But yeah, so it seems.
Yeah.
Okay.
Yeah. Ironically, the contradiction detector is often what people actually care about. Like we work with a bank, and they don't actually care that like their data joins or not. All they care about is whether or not they get a contradiction when they do it. And so they literally just sit there writing rules, try to integrate the data, check for a contradiction. If everything's fine, they just throw it away. They're like, oh, governance was fine. But if there's a contradiction, then they go off and they're like, oh my God, two clients are in the wrong ad campaign together, go fix it. And so it's funny, but we actually see in practice just as much interest in contradiction detection as actually integrating databases. I guess people will say they know how to integrate databases, but they don't know how to check for contradictions. So, yeah, it's funny what people actually want. Okay. And there's a question in the chat. Can you give me a reference to the complicated proof, please? Yes. So the recent paper we wrote called Fast Left Con Extensions Using the Chase. And what it does is says basically like what symbolic logic you write so that the process I described of you're doing substitution and like model completion actually gives you what the left adjoint should be. And so that paper, Fast Left Con Extensions, it goes through a number of examples of this. And for those particular examples, it uses results like, since this functor is faithful, the induced sigma will be also faithful. And so some of those conditions are worked out in Fast Left Con Extensions using the chase. Some of them will be scattered in the literature before that. The algebraic databases paper that was with Patrick Schultz and Christina V and David Spivak, that had some things too. And then there was at least one MIT student that did like a thesis that was trying to do something like that. Like they were trying to capture conditions on F that ensure that you never get non-conservativity in sigma F, but that actually turns out to be impossible. Like we've never been able to, or there's no decidable condition on F that would like prevent non-conservativity from possibly arising. Anyway, I can follow up offline. Like there's no shortage of papers to work on, and like, freaking David, there have been occasions where he's forgotten he's written textbooks on this stuff. I'm like, David, can you solve this? He's like, oh yeah, I have a whole textbook on it. Here you go. So, for all I know, that there's going to be a textbook on it. Okay, I'll end with this since we're running out of time. We talked mostly about functors today, but there's this thing called a profunctor that exists in category theory. It's not used as often, but it turns out that profunctors, their presentations look exactly like collections of relational conjunctive queries. And again, I think like this must be God doing the universe or something, right? Like this can't be a coincidence that relational algebra and profunctors have the exact same syntax. And so our tool actually uses profunctors more than functors, just because our users tend to know SQL and relational algebra. Anyway, I guess the point there is that instead of delta sigma pi, instead of 3 things, you get 2 things. We call them evaluation and co-evaluation. But, database theorists have not discovered co-evaluation. That's a new one. Like you can implement it using what are called chase algorithms, and, you have to go beyond relational algebra. But yeah, I guess the point in practice is that we actually use profunctors. Those look like SQL code. They do the same kinds of things. Here's a way to split up like that same example with a profunctor. You'd say, populate N1 using a join, or no, populate N1 by just scanning N, populate N2 by like scanning N. And then there's a little bit of extra data you have to provide that, like, I won't get into details, but it's basically like the discovery here was people can use SQL syntax to define profunctors, and that lets non-technical, non-category theorists use our tool. And so most of what you see like in our product manual and stuff will be using profunctors rather than functors. But the same kind of the stuff you can do. So anyway, with that, yes, so I can show the tool now. We have about 5 minutes left. There's a ton of other stuff here though, like just in the literature, like, what do you do when you need more than equations? How does this compare to SQL? Like there's cool stuff about like the growth and deconstruction, how you can turn data into metadata in this way. And like there's a whole, how does this relate to lambda calculus? And can you integrate data with pushouts? And like there's a huge just amount of stuff that I haven't talked about today that like, if you'll have me for a second talk, I'd be happy to go further or talk with people offline. And then, yeah, I guess just to conclude in the 5 minutes left. So here's the actual tool itself. You can download this on categoricaldata.net. The example we were doing, like from today, it's written down here. Like here's our 2 tables. Here they're T1 and T2 rather than N1 and N2. It's a little bit more, it has social security numbers too. Here's your schema mapping. There's a little lambda syntax. One of the questions we glossed over is like, what do you do when you have user-defined functions and you want to send like first name to first name capitalized? And there's the math says what to do there. And so the same stuff that you saw today is all done in the tool. There's some graphical components to it. Like you can see instances and presentations you write down. One of the examples I like to give is a Cayley graph, just demonstrate just how powerful the theorem prover is. Here's a finitely presented category. A schema has 1 object, 4 generating arrows, and then this system of equations. Does anyone recognize that this is a presentation of the quaternions? Like you just copied it from Wikipedia, but the theorem prover in here can go in and it can draw the Cayley graph bounded. But the point is, like, here's your 8 things in the quaternions, like I, J, K, and 1, and then negative I, negative J, negative K, and then negative 1. Like here's their, so the theorem provers we have are sufficiently powerful enough that like you can do things like that in this tool, in a way that, we haven't no one's ever actually come to us with a database in practice and been like, hey, I have a Cayley graph. But like the point is, like the theorem provers are all, like we wanted to illustrate what happens if you just like put theorem provers everywhere and like just sort of do the categorical algebra without regard for how hard it is. How far can you go? The answer is like this far. We've got like group theory in here. So for you guys, like at a technical level, what could you use? Like this is open source. You could potentially use like the theorem provers and the rewrite engines. And like if people are familiar with Knuth-Bendix completion, like it's doing that. Like it's taking, oh, here we go. Like it can take the three equations of group theory here, and it does like completion on them to get a complete set of rewriting rules. So like, yeah, we run out of time, but like under the hood, how does this stuff work since it's all computer algebra? Well, a lot of equational reasoning, and that turns into rewriting in the way you would expect. So we do a lot of Knuth-Bendix completion, a lot of critical pair analysis, a lot of like, rewriting type of stuff. So anyway, and then, yeah, I guess I'll show one more thing, which is just that it's all integrated with you're not forced to like axiomatize natural numbers. You can borrow those from like Java and stuff like that. So it's not just equational systems that you can write down. We give you the ability to bind into programming languages and use those as like abbreviations for huge numbers of rewrite rules. And so an example I always give is like, say you have employee department data, like I showed in the talk, it looks something like this. You have maybe a handful of missing data, but here's Al, Bob, and Carl. You just come in and like you just delete a bunch of stuff, delete, and then you run it again. Like the inferencing engine, like it, doesn't freak out. It just keeps going, and it like gives you these partial symbolic answers. Like we had a cumulative age column that was summing the ages of every employee and their managers, and like, well, what does that turn into? It turns into like symbolic results. Like this employee's cumulative age, I don't know what it is, but it's this guy's age, unknown 8 plus this other guy's age, unknown 9. And so like the rewriting permeates the data model here, and you get terms in your database that are rewritten based on the equations that you have. And we have to deal with things like which term and equivalence class do we display or serialize to a database, and like anyway, it's all rewriting under the hood to make this stuff work. And so I'm hoping for more dialogue with you guys. Seems related to what you all study. So anyway, I guess with that, I'll stop. I think I was told to stop at 15 after. So yeah, thanks.
Excellent. Thank you very much. Yeah, so any questions? So we had another question from YouTube, I think. Can you see the chat, Ryan?
Yes. Are there other tutorials, yes, for CQL that are not published as papers? So the answer is yes. Like we've tried our best at least. And so there's like a getting started page here. Like we try to make it so that the IDE itself comes with built-in examples. Like when you click on one of these, like it just pops up code. Categorical data, .NET has some tutorials that are better than papers. But I mean, I guess really we need more. Like we can tell we're a group of rogue academics. So anyway, yeah, check categoricaldata.net. And if you struggle, feel free, you can send me a question and I can help. Like I don't mind doing that kind of thing. We have an email list, it's low traffic, you can get to it and that kind of thing. But yeah, anyway, okay. Other questions? If someone without a categorical background would like to use CQL. So good question. I claim that you can learn all this stuff without knowing category theory, that like the way that, a profunctor looks, it looks enough like SQL that you can just pretend you're writing SQL. And so like I claim that yes, you should be able to use this tool if you have either a category theory or like a data background. Like if you don't know SQL, I think it'd be tough, right? Like none of this syntax would make sense. But if you don't know category theory, like you can kind of, like if you ignore this little part here, then the rest of this basically is SQL. And so I think the answer is yes. Like if you stick to those parts of CQL that look like SQL, you should be able to use it without knowing category theory. And I'd be happy to help test that hypothesis. Like if you want to go try that, and like tell me what works and doesn't, like I'd be curious to know like where you struggle and where you don't. Like we want to make it available to people that don't know category theory. And we're trying to figure out, is there more to do than just make syntax that looks like SQL? So a tester would be most helpful. Thank you. Other questions?
Nick, go ahead.
Thanks a lot, Ryan. That was really interesting, and I think we would be glad to have you again. First of all.
Oh, my pleasure.
So I'm really trying just to understand, because so the carrier structure of, I mean, a schema is such, of course, just some at the face of it, some particular kind of, well, I guess labeled graph of some sort.
Yep, an algebraic theory of a particular kind. So there are restrictions that say like you can't, like you can have an arrow from men going to string, but you can't have an arrow going from string into men, for example. So it's not arbitrary, but yeah, these are just algebraic theories. But this is true.
Well, but I mean, then perhaps even some sort of attributed structure. But
Right.
Then, of course, for our community is a interesting question: are those functors that you can write that are good functors just rewrites in a compositional writing category? So is it perhaps the case that those structures of functors that happen to be good? I mean, I wonder, I'm really curious, because I mean, we know how to rewrite graphical structures. And I'm wondering if there's a deeper link between what it means to do I mean, you do the functors sort of as total mappings of some sort. At least it looked like it was total mappings. So the question is, did you ever experiment? Because I mean, like with all the double push-out rewriting, for example, did you ever experiment?
Oh, yeah, I mean,
a deeper link?
Right. Yeah, I didn't get to cover like co-limits and stuff like that, but I guess so nothing we talked about today mentioned how to take two databases in and one database out. And so,
Exactly.
But you can use category theory to do that too, right? So first you integrate schemas using co-limits, like something like this. These are just graphs, but it's the same idea if you have equations running around.
Right.
And then similarly, you can use co-limits. You have to use sigma delta pi to kind of move your data around to get them into co-limit form, place where you can take them. But like we in practice, we just as often end up integrating data as opposed to moving it from one place to another. But it's the same idea. Like, there's a lot of connections between sigma, left con
Right.
and things like co-limits. And so here's a data version like that. Like here you're merging health record data. You got Peter and Paul and like blood pressure, heart rate. You have another database, partial overlap. Here he's called Pete. And so
Right.
you have another schema that specifies like the overlap, and then this is what the answer is. And like, we know how to get this using the same algorithms. Yeah.
For example, it would be just interesting to know, like, if I specify, if I weren't to then later use these schemas to actually model database, I were just to look at the schemas as some kind of labeled or attributed graph, and I were then to do a rewrite in our sense, I were to manipulate this graph in some fashion, I would be just curious if one could find that perhaps there's some consistency in how you do these functor constructions, and what classifies as a rewrite, where perhaps you could, for example, if you drop some part in the data structure, or you insert a new data structure and so on. I mean, that would be quite interesting, I think.
Oh yeah, I mean, all the nitty gritty details are written down if you want to go for it. Like there's a paper called Algebraic Data Integration that focused a bit more on the syntax side and like how the theorem provers work and that kind of stuff. But yeah, I mean,
and if I can afford one more question, more in the direction of what Raiko asked earlier. So I guess sometimes your schemas, I mean, you would also have to express some like certain kinds of some consistency constraints that are not directly expressible just in the simple sort of schema you had. So is there a language on top where you can say, for example, whatever you do, never map, I don't know, people to
we
animals? Or?
Like we are constrained to use like algebraic theories and functors and whatnot.
Right.
So but I mean, that gets you pretty far. Like here's an RDF example that does friend of a friend. Like if you've seen this one, you know, you have people and organizations and they have relations like this person knows this person. And so here's one where everything is relations. So we had to encode it using spans. You can see like the dual legs here, but you know, anything like that. I guess maybe the question is, how far do we go once you're outside of equational logic? So
exactly.
We like to use a language called regular logic. That's a name category theorists gave it. It's existential horn clauses, basically.
Okay.
So like data log with existential quantifiers on the right. The reason is that the most expressive logic for which you can do what we call a chase algorithm. Like you can, with this kind of logic, you can take a model and repair it and get a unique answer that satisfies the equations. If you have more expressive logics, you don't get that anymore. So a lot of like our use of this particular logic, existential horn clauses, like database theorists just use that one to do their own work. Like everybody who's doing data integration kind of uses the same logic. And it's because it gives you model completion. And so one of the papers we wrote is how to implement the sigma operation using model completion in this logic. That was the fast left con extensions using the chase paper. The model completion being called a chase algorithm. It kind of chases your missing values around and determines them and so on. So anyway, yeah, so this, we like it when you're in this logic because then model completion works. If you're not in this logic, we got a problem on our hands because conceptually what you're doing isn't really data integration anymore. Like if there's ever a choice in how your data, like what the answer should be, then it's like bad for data integration where there's always supposed to be like one, everything's supposed to be unambiguous. But yeah, it's a good question. And then these have different theorem provers than the equational logic. And what's cool about these is they break into, I'm going to do one more slide and then I know we're over time, but because there's a deep connection between that logic and the notions of database and whatnot. Like every formula in that logic is actually the same thing as a natural transformation of databases. Like the reason that logic is useful is that it encodes natural transformations of databases. And so like there's this thing in database theory called a frozen instance or a canonical instance. And like they have all these papers that are like, here's your logic, here's your corresponding databases, here's your databases, here's your corresponding logic. And what David Spivak figured out like before we brought like database rigor, like he wrote a whole paper about this phenomenon using like the language of algebraic topology. He talked about like lifting problems and stuff like that. But anyway, so the reason we use that logic, like there is a deep reason and it connects what we're doing to like every other branch of math. Like everybody's using this logic for the same reason. And I think it's because it admits model completion and it's the biggest one that does. Like all category theory universal properties fall into this fragment. It can't be a coincidence. And yeah, so anyway.
Very interesting. I leave the floor to others to ask questions, but we should discuss more. Yes, thanks.
I just want to make a side remark. This is exactly the format you have in these sketch axioms from Mackay.
Yes, that is not a coincidence.
I mean,
we're all doing the same thing here.
Yeah. Okay, good. That was
to the extent anything's new here, it's more like the connections to SQL and how data migration works. But yeah, like all this sketch stuff, it goes back decades. We didn't invent that. Yeah, I want to be clear that the sketch stuff predates this. Yeah.
Okay, good.
Cool. Okay. Well, with that, thanks for having me. And yeah, I'm happy to come back.
I have
sooner rather than later. Yeah. Oh, another question. Yes, please.
I have another question or hypothesis anyway, because we talked about the relation to graph rewriting. And double push out. I think most of what I've seen anyway is a bit orthogonal to graph rewriting in the sense that, I mean, there's something like which we call typed graph transformation or typed graph rewriting, where a typed graph is essentially like your schema. I mean, it's the kind of dual point of view because in the typed graph, we look essentially at the fibered structure. So the instance graphs are what your database states essentially, and they're mapped into the type graph by graphmorphism. Whereas you look at this in a kind of what I would call the index point of view. So mapping the signature, if you like, the schema to the instances. But you know that these are essentially dual to each other, so you can sort of swap one for the other. So
right.
And if you have
show this slide,
sorry,
I wanted to point that out, that like, yes, the fact that you can go back and forth and get graphs out of the data. I didn't talk about that in the talk, but like that's like the first thing you might use in practice if you're dealing with RDF or.
No,
so here's an example, right? Rather than the tables at the bottom, like why not just use this graph at the top and frame everything in terms of graphs? Sometimes that's what our people do, like as a proof technique. They're like, all right, we're going to work with the graph form first. And like, this is why we talk so much with the Apache Tinkerpop community. Like they're a bunch of graph people and like, so anyway, sorry, I didn't mean to interrupt you, but just, I want to let you know that like, that is a whole other thing that is, and like David Spivak uses this form a lot.
Yeah.
And like, I don't know why those fibers are so nice or what they're helpful for, but like, I'm glad that they produce the answers I want. Yeah. Anyway.
It's just
yes, let's talk more about that.
Thing, I suppose. Two different representations. Sometimes it's nice to have everything in the same big space and type, and sometimes it's better to sort them by indexing, I think. But anyway, so what I was going to say was, as far as I understand the connection, so between different categories of type graphs. So you have a category of type graphs for a fixed type graph, which is basically the fiber over that schema, if you like. And there we're quite familiar with at least two of the constructions that you mentioned. So obviously you have if you have a morphism between type graphs, you get a similar projection construction by means of I have to be careful. So one is a composition with the morphism between type graphs, and the other one is a pullback.
It's probably delta and sigma running around there.
Projection
delta is the pullback.
Yeah. So and these are the left and right adjoints. But okay, so there's only two of them. So we are quite familiar with two of these functors. That's what I'm saying. But you have three. So I haven't quite figured out yet what the third functor would be in our setting. I'm pretty sure we can interpret that in the typed setting as well, but I'm not entirely sure exactly which one it is. So I think
you're not the first person to notice that. Like when we tell logicians, oh, we have adjoint triplets here, they're like, oh, you mean you have something besides this one? And they're like, what the hell could that be? So yeah, it's semantics. I guess the counterpoint might be, since it's doing what relational join does, like the semantics can't be that complicated. It's more the fact that it exists at all, like the fact that those joins stand in the relationship you want. Like that's kind of the surprising part, I would say.
Yeah.
No, this was actually the easy one to implement. Yeah.
I'm not questioning the meaningful, that this is meaningful. I'm just puzzled because we haven't, I can't think of the kind of corresponding, and the structures we're dealing with are not any more complicated than the ones that you have. I mean, most of the time we have graphs without equations. Yeah, so it should be even more obvious in our case what those three.
Maybe that means we need a joint grad student or someone to work all this stuff out. Like, that sounds like a paper opportunity.
Maybe a bit of paper and half an hour to think about it. But yeah, so okay. But what I'm saying, so this is as far as I managed to make the connection. So the pi puzzles me a bit at the moment. So I maybe think about this later today. But what our rewriting does is most of the time is orthogonal to this, because we look at rewriting the instance graphs for the purpose of describing dynamics on them, for example. Yeah, to say that the instance graphs changed somehow. I mean, either evolution over time or some kind of, I mean, if the instance graphs represent models, then maybe these are model transformations. Yeah, so whatever reasons you may have for your graphs to change. So we basically program changes on these graphs by means of rules. But then there's also an interesting question. If you see the evolution of graphs or the change of graphs within the same schema, and then you have a projection or you have a migration one way or the other, what can you do about sort of translating the changes on those graphs across these migrations. If I'm using your terminology, so the relations between schemata basically, and the rewriting on the graphs within the schemata. So that's why I say our rewriting may often be orthogonal to what you are doing.
Like I know there's a connection because the way you implement Sigma, for example, naively uses a ton of rewriting. Like I can't speak to what you just said specifically. I do know that in the products we sell, they often, it's not just data integration. It's often like, give us your SQL queries, give us a schema mapping, and we're going to give you new SQL queries back that like change the schema that they're on, but give you the same answer. And so like, I know that there are like the products we sell are doing like rewriting on SQL code, like for our clients. So I know there is some value in like doing rewriting straight up.
Yeah.
But I don't know the technical connection. I think we need to like a grad student or a postdoc or something to work out like how this connects to graph rewriting. It'd probably be a good exercise. Like, we could pull resources maybe or something, like we have our own interns, but I think it'd be good to push on.
Okay.
Because, we don't want to be reinventing techniques either. Like we just want to use the rewriting you guys already have. Like we don't want to implement this stuff from scratch. We just want to make money off of it. Yeah. So, yeah.
Okay. Yeah. Sounds interesting. Maybe that's a good motivation to have another seminar. Maybe we need to discuss a bit or agree exactly what directions that could take. But clearly the role of rewriting in your framework here, I mean, you didn't have much time to address, even if I can, sort of imagine what that might be, but only at a very high level, I guess. There were lots of other things on your list, of course, that sounded interesting. So.
Okay. Cool. All right. Well, then I guess, whenever you'd like, happy to come back. We can dig more into like how you implement this with rewriting and that kind of stuff. Maybe form up a plan for what people could look at. But or just talk more. I mean, there's the other 8,000 pages of this, right? So up to you guys. But yeah, I'm happy. The time isn't a big deal. Like, I'm up pretty early anyway. So the sun is risen. That's cool. Yeah.
Okay, excellent.
Cool.
All right. So then I think this is probably a good time to finish the official part of the seminar. And thank you again, Ryan. It was very good discussion as well.
Okay. My pleasure. Thanks for having me. Maybe
you can, Nick can briefly say what happens in a couple of weeks.
Yes. So first of all, thanks also to Ryan from my side. Really excellent talk, and I'll just send you an invite link again. We should have you hopefully again, maybe in the spring or so.
Cool. Sure.
Yes, and then
I'll
in
drop
2 weeks,
then, so you guys can talk. Okay.
Yeah, no, but so thanks to everybody who attended. We'll now stop the live stream. Should you want to have a quick word on Zoom, we might stay for another few minutes. Otherwise, maybe see you in 2 weeks again for a talk on graph neural networks by Francesco Di Giovanni. I hope I pronounced this correctly. And thanks again, Ryan. Thanks everyone for being here. And I'll now stop the YouTube live stream. Thank you.